I posted a midterm 2 survey. Well, we're so close to the final, I think it's unreasonable if I ask like additional suggestions to the lectures. But I did add 2 questions, remind you that the end of quarter survey of the class is coming up. So do fill them in if you have the chance. One of your graders hadn't finished their part for the midterm 2 grade. So I'm not sure if I can post your grade by the end of today. So I'll probably post it next Monday so you can enjoy your Thanksgiving. What else? Any administrative question before we get started? Yeah.
Where's our final going to be?
It's decided by your registration office, so you can see it on your MyUCLA site. I'll post more information next Monday.
It has 2 locations on there.
Yeah, I'll post more information next Monday. Yeah, like what we did for the midterm 1 and 2. So next Monday, I'll be posting, a long message saying like where your final is going to be, what's the coverage, what's the format, what are the review recommendations, etc. Any other questions? Okay, so let's get started. In our last lecture, we went over the mechanism of this alkane halogenation via a radical chain reaction mechanism. We then raised the question of what is the origin of selectivity in these alkane halogenation reactions. We went over 2 different factors, one being statistics, right? So how many primary versus secondary CH groups are there ready to be abstracted, or thermodynamics, or the relative stability of the radical, carbon center radical that's being generated. But at the end of our last lecture, we raised the question, or be like, using statistics and the thermodynamics are not enough to explain the differences between the relatively low selectivity of chlorine abstraction versus the bromine abstraction. So the bromine halogenation is way higher in selectivity comparing to chlorination reactions. So from there, we'll introduce a third factor, which is kinetic factor. So now we're talking about the actual transition state. Or when we say a transition state, we're now dealing with partially broken and partially forming bonds. In this case, if we're looking at bromination as an example, we'll see that in the transition state, we have partially breaking CH bond and partially forming HBr bond. If we put it onto the energy diagram, we're expecting something like this. Right, so read the Hammond postulate again that tells us information about the position of the transition state. Or hypothesizing, or we're stating the relative species that are closer in energy are also closer in structure. So for an endothermic reaction of which your product is less stable comparing to your reactant, in our last lecture, we also went over how to calculate the thermodynamics or delta H of the reaction from the bond dissociation energy of your reactant and product. So for an endothermic reaction, or we have positive delta H naught, right? So that's for our bromination reaction. If we zoom out onto my reaction coordinate surface, so on the y-axis, that's the heat of the reaction. On the x-axis, that's our reaction coordinate, starting from reactant to product. Now, in here, what is my reactant? My reactant is like my propane, and my product will be a carbon center radical and HBr. Let's not worry about selectivity at the moment. We'll apply the selectivity later on. For this endothermic reaction, my product is higher in energy than my reactant, thus my transition state. Now, as a transition state, it needs to be higher in energy comparing to both your reactant and product, right? So my transition state will be closer in energy to my product because this is a endothermic reaction. using the Hammond postulate, will derive, or we can propose that the transition state will also be closer in structure comparing to my products. And indeed, we can calculate what the transition state looks like using quantum mechanics. And here comes from my quantum mechanical calculation. I don't expect you to know the actual number, but we calculate the bond length between your carbon and hydrogen is 1.94 Armstrong, and between your hydrogen to bromine is 1.52 Armstrong. In comparison, if we look at the CH bond length in the original reactant, that is 1.110 Armstrong, and the HBr bond length in the product will be 1.42 Armstrong. So comparing to the relative differences or the relative changes of your CH bond and your HBr bond, it's safe to claim that indeed our transition state is a later transition state that resembles the structure of the product. All right, so the Hammond postulate is the physical organic chemists come up with the postulate based on pure chemical intuition. But now with the development of technology, we're in a better position to validate the Hammond postulate using quantum mechanical calculation. And here's a proof that Hammond postulate at least works for these hydrogen atom abstraction transition state. And what about chlorination? So let's look at the chlorination energy profile and think about what the structure will look like. Again, the energy profile of my chlorination reaction will have your energy on the y-axis, reaction coordinate on the x-axis. My reactant is the same, and the product will be what we are expecting, which is the carbon center radical and HCl. But since we calculated the chlorination reaction as an exothermic reaction, or the reaction releases heat, we're expecting the transition state to be closer in energy comparing to my reactant, or we're expecting the transition state using the Hammond postulate to say the transition state must also be similar in structure to my reactant. And we do the same quantum mechanical calculation. We see that the the carbon hydrogen bond is like 1.47 Armstrong. The hydrogen chloride bond is 1.42 Armstrong. And now we can compare these two optimized transition states side by side. What do we have? First thing is we see the carbon-hydrogen bond in the bromination transition state is considerably longer comparing to the carbon-hydrogen bond in my chlorination transition state. Right, and this one, the hydrogen-bromine bond is only about 0.1 Armstrong difference comparing to the ground state HBr. Alternatively, this 1.42 is like more than 0.14 Armstrong difference comparing to the bond length in the HCl ground state. So it's safe to make the conclusion, right? So we use quantum mechanical calculation to further validate it, the Hammond postulate, in the halogenation reaction, that my bromination reaction or an endothermic reaction will have later transition state or transition state closer to products. Alternatively, in an exothermic reaction, my transition states are closer to reactants. All right. And as a side note, we were saying HBr is a weaker bond comparing to HCl. And judging by the bond length, we see that in HBr, the quantum mechanical calculation is predicting the HBr bond being a longer bond comparing to my HCl bond, also fulfills our expectation of HBr being a weaker bond. Yeah.
So is this like pretty much related to electronegativity of the species?
Yes and no. It's more related to the size of the species. All right. Now we have the Hammond postulate. Let's apply the Hammond postulate into explaining of the reactivity, the selectivity differences in bromination versus chlorination. Remember, experimentally, we observed that bromination is way more selective comparing to chlorination. And that's related to the shape of my potential energy surface and the transition state structure. So again, for bromination, we have endothermic reactions. So on the profile here, we see the transition state are closer in structure than your product. Let's say we calculated our product, the relative thermodynamic stability of my product is different by 13 kilojoule per mole. In my reactant, however, we're talking about abstraction of CH bond of the same molecule. So reactant is the same, no selectivity whatsoever. So for bromination transition state, because they are closer in structure to the product, they are also closer in energy to the product. Or in this case, you don't have to be quantitative about the number, but you could expect these transition states to be quite different in energy, like what we would observe in the product. Or if we put it on writing, we're saying the late transition states are closer to product, and hence the delta E double dagger, so that double dagger is referring to the delta E in the transition state between transition states are similar to delta E between products. All right. Alternatively, if we're looking at the chlorination example, what do we have? We have my exothermic reaction, or the reaction is downhill. My transition states are early transition states that are closer to reactants. That means the delta E naught, or the change, the delta E double dagger, or the change, the difference in energy between my two transition states for chlorination will be similar to delta E between reactants. And what are my reactants here? There's no delta E in my reactant. My reactant is, in both cases, is propane reacting with chlorine dot. All right, so taking them side by side, now what do we have? We now have a clear picture into the effect of kinetics, or the position of transition state, on the overall selectivity. Right, my bromination is later transition state, much similar to the product, and hence the bromination is a more selective reaction. In comparison, in the chlorination, my transition state is an early transition state, and hence much likely to behave as my starting material or my reactant and not being selective. Right. So the application of Hammond postulate doesn't need to be quantitative for this lecture. You don't have to explain why this is 97, why this is 4.5, how does that 4.5 correlates with the 4 kilojoule per mole differences. It's more important to get a qualitative expectation. It's when we're looking at two reactions and we tell you the thermodynamics of the reaction, how to use that thermodynamic of the product to predict the position of the transition state and hence the selectivity in a qualitative fashion. Yeah.
If in earlier slides you said that chlorine has to be exposed to natural light or heat for the reaction to happen, why is it considered exothermic if you technically have to add heat to the reaction for it to happen?
So to answer this question, first of all, you have to think about elementary step when we're talking about specific selectivity. Now, if we're looking at the full reaction mechanism, then we're saying, okay, so there must be an initiation step to form the chlorine radical. Now, this initiation step requires heat or light to crack or homolytically cleave the chlorine-chlorine bond. But upon formation of the Cl dot, we're initiating a chain reaction. Meaning if after the initiation you take the light or heat away, the reaction will continue to proceed because of these steps are chain reaction mechanism in the propagation step. So when we are talking about selectivity, it's more of talking about selectivity of every elementary step, not of the entire reaction. Now, of course, the selectivity of the entire reaction is reflected in the selectivity of each elementary step, right? So in this case, the selectivity is determined by this step where your chlorine dot comes to abstract the hydrogen. And the rest of termination, they have little effect on the overall site selectivity. So try not to mix these two terms. It's selectivity of overall reaction is related to selectivity of elementary step, and we are focusing on one single elementary step to explain the overall selectivity. All right. And what do we know so far? Well, as a quick summary, we went over 3 different factors that control selectivity in alkane halogenation reaction. We have statistics, which just count the number of hydrogen atoms. We have thermodynamics, that tells us the relative stability of the carbon-centered radical, tertiary being more stable than secondary than primary. Then we have kinetics, right? Hammond postulate. For an endothermic reaction, transition state closer to product. Exothermic reaction, transition state closer to reactant. Ready to apply what we learned into predicting selectivity in a new reaction? Let's try it. So here I'm giving you the reaction, which is a fluorination reaction. The question asks you to compute the heat of reaction for abstraction of a primary hydrogen and a secondary hydrogen from propane by a fluorine radical, or F dots. Right, so the 2 reactions are listed above. First question, calculate delta H of each reaction. Second question, qualitatively describe how selectively do you expect the free radical fluorination to be. And C, well, roughly predict what is the product distribution you would expect to obtain from the free radical fluorination, assuming monofluorination. All right, let's work on this together. First thing first, I give you the bond dissociation energy of your propane on the primary CH or secondary CH and also the HF. So the first step, I'm just gonna do it on the board. And if you are watching the recording, the annotated note also has the answer. So first question, calculate the delta H of the reaction. So the first one, let's say the F dot abstract a primary hydrogen. H naught of the reaction will be the bond dissociation energy to break my primary CH bond, which is 98, minus the bond strength of the HF bond that the bond dissociation energy of the HF bond that we're forming. So minus 136. Plug that into the calculator, that's negative 38 kilocalorie per mole. Right. And again, this is my BDE of primary CH. This is BDE of HF. Same thing for the secondary CH. And if we want to do the arrow pushing, you don't have to. Delta H naught equals to my, let's see, 95 minus 136 to be negative 41 kilocalorie per mole. All right, with me so far? Just calculate the delta H of the reaction from BDE of your reactant and product. A quick review. Second question. Based on the calculated delta H of this reaction, how selective do you predict this reaction to be? So remember what we did, right? We have probability, which is the same for all the cases, and we have thermodynamic, relative thermodynamic stability. So in both cases, the difference in your product is always 3 kilocalorie per mole, whether it's fluorination, chlorination, or bromination. The difference comes from the kinetics, or using the Hammond postulate. So for the second question, using the Hammond postulate, we were stating if the transition state is closer in structure, they must be closer in energy. So if we plot the energy diagram of your reaction profile, or reaction coordinates, so this energy, we can put H as well, which is some form of energy. Now this reaction is a highly exothermic reaction, way more exothermic comparing to our chlorination reaction, because HF is such a strong bond. So that means if I put my reactant, which is propane, and S dot somewhere here, my product will be all the way down here. And their difference will be relatively small if you compare it to the overall thermodynamic favorability. Like the difference here is 3 kilocalorie per mole. But the overall reaction is like such a downhill process. Right, so the differences between these two are up to like 38 for my primary and 41 for my secondary. So in this case, because we're looking at such an extremely exothermic reaction, we're expecting my transition state to be a super early transition state using the Hammond postulate. And what else do we know? Now, because my transition states are super early, the differences in energy between my transition state will be much more similar to my reactant, and hence the difference in the transition state will be very small. And to answer that question, do we expect the reaction to be very selective? No. Right. Because of these super early transition state and using the Hammond postulate. What about the third question? Now the third question asks us to sort of predict the product distribution. Now using what we have discussed in the first and second question, remember we have three factors controlling the overall selectivity. We have probability. I think I'm spelling it wrong, but. And when we're saying probability, we're just simply counting how many of these hydrogens in my starting material are primary, how many of them are secondary. So I have 6 primary hydrogen and 2 secondary CH. The thermodynamics and kinetics we have already discussed in my part 2. So in this discussion, we come to the conclusion that based on the thermodynamics and the kinetics, like the analysis of these transition states, we're expecting thermodynamics and kinetics to have little effect on selectivity. And then my probability becomes my dominating factor, because the rate to abstract a primary or a secondary hydrogen becomes effectively the same to each other. We can then come to predict the product distribution to be, well, 75%, because it's 3 to 1. Right, so 75% abstraction of primary CH, 25% abstraction of secondary CH. So we're predicting the actual products that will become the primary to be 75% and secondary to be 25% based on the probability itself. All right. So for this kind of question, what if we go, instead of going up to fluorine, thinking about the same kind of question, now we're asking this question again for iodine. Are we expecting the halogenation with iodine to be more selective or less selective comparing to the reaction with bromine? Raise your hand if you think it's more. Raise your hand if you think it's less. Yes, right, so my iodine is even a weaker bond, so the reaction even more endothermic. We're expecting even later transition state and hence better control over the selectivity. Later on, chemists also developed that into what we call the reactivity-selectivity principle, but this one is, the origin of that theory. How do we feel so far? This is the first time you're predicting a reaction outcome using chemistry knowledge only, without doing experiments, to get like numbers, right? Yes?
So I understand why products that are energetically closer to the transition state, like they look alike, but I'm just wondering, why is having a later transition state, why does that give you more control?
So that goes back to the shapes here, right? So the origin of selectivity comes from the difference of your secondary radical versus your primary radical, right? So your secondary radical is more stable than your primary radical, and hence we have the difference in energy in my reactant, but in my products. But in my reactant, we have no difference. It's just a propane. So that is why if my transition state is closer in structure to my product, it will be closer in energy with my product, both of them, right? So the later the transition state, the more likely we'll be able to distinguish the difference because the product is different in energy. All right?
So if you have your transition state super early, what's happening for the rest of the reaction between transition state?
It's after you pass the transition state, it's straight downhill. So the transition state is, the highest point along that single reaction coordinate surface. The reality is way more complicated because these reactions coordinate surface is multidimensional. Here we're just taking like one slice of the more complicated potential energy surface along the reaction coordinate. And the transition state is the highest point along that coordinate. All right. Let's move on to talk about more of halogenation reactions, which is, well, we've been talking about selectivity. What about stereoselectivity? So, will this reaction be stereospecific? Now, the way to put it is thinking about what is the nature of this carbon-centered radical, right? So, the final bond formation process is when you have another molecule of Br group, the radical will form the bond between the Br either from the top or from the bottom. Note that in this non-asymmetric or fully symmetric achiral environment, there's no way your radical knows where that bromine molecule comes, whether it's from top phase or bottom phase. So typically, for the halogenation reaction, we're expecting formation of a racemic mixture. So 50% R, 50% S. All right. And next up, so far we went over alkane halogenation, so breaking off a CH bond, sp3 CH bond. Likewise, we can do the same for allylic molecules. A quick review on what is allylic molecule, or what are we talking about when we're saying allylic allylic system. Now, these bonds that directly attach to a double bond are called vinylic CH, so VINYILC. So the vinylic CH bond are pretty strong CH bonds with BDE equals to 111 kcal per mole. So in comparison, if we look at the sp3, the terminal CH, that's 98. The secondary sp3 CH bond, BDE, is 95 kcal per mole. So the vinylic CH bond are pretty strong bonds. However, if we're looking at the allylic CH, or the carbon that is adjacent to a double bond, these allylic hydrogens, or allylic CH, have a much weaker bond dissociation energy of 89 kcal per mole. All right, so the allylic CH bond are much weaker than your vinylic CH and also much weaker than your sp3 CH bond. So that means when we have a reaction coming in, like a bromination or chlorination reaction, abstraction from the allylic CH bond is much more likely to take place. But in this case, we're facing a problem. So far we were talking about alkane reacting with Br, right? So alkene reacting with halogen. according to our previous experiences, we know alkanes are pretty inert chemicals that do not react with a neutral form, halogen, or whatsoever, right? But when we have a double bond, we have discussed multiple reactions that can take place with a double bond. So this is one of the cases that depending on what do you want in your product, you want to use different kind of reagent to control the reaction selectivity or to control the type of reaction you want it to proceed. So in this case, if we start from a cyclohexane, instead of using Br2 as the reagent, like if we want to achieve allylic halogenation, we cannot use Br2 with light or heat as our reagent because of potential side reactions that can take place. All right, so these are the things you want to take consideration when you're writing total synthesis processes. Like you want to eliminate as much side reaction as possible. As a quick review, thinking about what might happen if you have cyclohexane, you treat it with Br2. And naturally, you'll have the electrophilic addition to form that carbocation, and now this one is a bridged carbocation. You have 3 resonance structures, and then another Br minus will come in and form the new dibromo substituted cyclohexane with a anti-selectivity. And if you draw out that anti-selectivity, you can also link this into like the chair conformation we discussed. We want to be anti-stereo specific, so my 2Br group will be on opposite face. So when I draw it, the more stable conformation will be this one. All right, so this is more like comprehensive, using sort of everything we discussed, like earlier in the quarter, in the middle of the quarter, and now we're talking about this as a potential competing reaction. To prevent the dibromination or the electrophilic addition onto the double bond from happening, halogenation or allylic halogenation typically use NBS or this N-bromosuccinimide as our reagent. So this is acting as an indirect source of Br dot. And let's look at the actual mechanism of the allylic halogenation. These should be something you already know. It's the same type of radical chain reaction mechanism. Like what we did, right? I have already write it out. I'm just gonna walk this through with you and also add arrow pushing along the way. First step, initiation. Remember, initiation is you start from a neutral molecule, homolytically cleave a chemical bond, the weakest chemical bond in the molecule, to form 2 radical species. All right, so this is forming a one bromine center radical, and then the succinimide radical, or the nitrogen center radical. In the propagation step, we have my cyclohexane. I write it out one of the allylic hydrogen. You can write other allylic hydrogen as well. In the propagation step, the electron in this CH bond form a new bond between the hydrogen and the bromine dot, and the other electron goes onto the carbon to form the allylic radical. When you're drawing the allylic radical, as we introduced earlier in the quarter, you can either draw it as a resonance structure, or you can draw it using that dashed lines to show the radical is being delocalized over all 3 carbons. Upon formation of the carbon-centered or the allylic radical, we have the second propagation step, where that carbon-centered radical is again attacking a Br2 if it is present, or in this case, it's succinimide actually, and to form the product, which in this case I probably should have write it as like nitrogen and break it to form the nitrogen center radical. And next up, we have different termination reactions. Either you have Br dot, might meet Br dot to form Br2, and this Br2 might also go back to further react with your carbon center radical. You have the allylic radical terminate with Br dot. Or you can have the dimerization of your allylic radical species. So now obviously we have a question of regioselectivity. In this case, in the cyclohexene case, the regioselectivity is not a problem because my allylic hydrogen is pretty symmetric. If we're looking at a linear molecule, then we have a question in which position that radical is more located in, and hence when the second bond formation is taking place, where will that Br group go on to? Yeah.
So, I might be wrong, in the propagation step where you have the radical pushing here, radical pushing there, if the bond for the hydrogen is broken and its electrons are donated to that becomes
All of these arrows are single-sided arrow, where we're
forming HBr, like I'm kind of confused because like
we're forming HBr as a side product. I just forgot to write it. Yeah.
So I was wondering where the bond goes.
Okay. Thank you for the reminder. And now let's move on to talk about regioselectivity. So these are a quick review on the MOs of our allylic radical. So again, the resonance is good, but it's not the end of the story. The reality are these molecular orbitals, right? So we were talking about the middle one being the singly occupied molecular orbital, the one we should be focusing in. In this case, we're just telling you that if that on one of the carbon, if it has higher spin density, we're expecting it to have higher or faster propagation. So that means if we have this kind of linear molecule, the linear allylic molecule, or the other way to put it, this is the same as writing like this in resonance with this. All right, using the resonance structure alone, one would expect this terminal radical to be less stable, but it's not the case. That's why I'm highlighting the molecular orbital picture in this case, because resonance doesn't always work. In this case, when we are looking at the molecular orbital of this linear allylic molecule, we see there is a greater lobe on the terminal carbon, hinting that the terminal carbon will have larger spin density. So that means when we are predicting the reaction outcome for these allylic molecules, the terminal position, because it has higher spin density, it's easier to have the faster, it will have a faster propagation step from the terminal carbon. Or the other way to put it is if we look at the rate limiting step of the bromination reaction, so this radical adding onto the Br to form this terminal CBr, or this internal one adding onto the Br to form the internal bromination. The top one will be faster, and the bottom one will be minor. Now, for this kind of question, I do not expect you to know what the MOs look like. More likely, I'll give you the information in the question like what I did. I can potentially give you a calculated shape of the singly occupied molecular orbital with one lobe larger than the other. You're supposed to use this information to derive, it's like, okay, from reading the shape of the SOMO, I recognize that the terminal carbon has a higher lobe or a higher spin density. So from there, can derive that the propagation from the terminal radical is likely to be faster comparing to the propagation of the internal radical with a smaller lobe. So I'll give you that information, but it's your responsibility of linking the shape of the MO to the reactivity of the radical addition reaction. All right. And because I'm sort of running out of time, I'll skip the two slides below, which is like radical autooxidation. So I'll skip this one. And also the mechanism of radical autooxidation of polyunsaturated fatty acid. I'm not going to test you on these, but I mean, if you're interested, feel free to read more about it. I've 5 more minutes left, but I do want to highlight on this one, which is the radical addition of HBr to alkenes. So this is one of those examples. It's depending on what reaction condition you're using, even with the same starting material, you could expect different mechanism and hence very different selectivity. So remember, in this case, if we're looking at the reaction without peroxide, so we're looking at the acid catalyzed, we're looking at the normal Markovnikov electrophilic addition through a carbocation intermediate, or in this case, the reaction we're looking into is the double bond attacking the hydrogen, breaking the HBr bond to form a tertiary carbocation. You have the Br minus comes in and forms the bond to form my product with the Markovnikov selectivity, where your hydrogen adds onto the carbon with more hydrogens on it. That's a review. That's something you discovered before. Alternatively, with the presence of peroxide and treated with light. So whenever you see like peroxide and light, we are hinting this reaction is likely to be a radical chain reaction. So that means if we look at the mechanism of these radical initiated HBr addition to alkenes, we're looking at a completely different mechanism and hence different products. For example, initiation here, we form a radical, and this radical breaks the HBr bond to form the bromine-centered radical. In this case, in my propagation step, what do we have here is, well, the electron in the double bond forms a bond between your Br minus and electron goes onto that carbon center. Right, so we're forming the more stable tertiary radical comparing to the less stable primary radical. In the second propagation step, what are we forming is this kind of bond between your hydrogen and the electron goes onto the bromine. And we're generating the product here where your bromine is added onto the terminal position. You could argue that you can also form a bond between your internal radical with the bromine, but nevertheless, you can never form the Markov-Nikov hydrohalogenation product. And then you have the termination reaction, like maybe this one. You're regenerating, you're forming the dibromo substituted product as a side product. So this is a scenario that depending on the reaction condition, you can have different kind of reaction, hence different kind of reaction mechanism and different selectivity. So when you are writing organic chemistry reactions in total synthesis, pay careful attention into what is the reaction condition, what is actually happening. And as a quick summary, this one we basically only tells about three different types of reaction. One, we focus a lot in this radical halogenation. It's a unique type of chain mechanism involving radicals. Went over allylic bromination with MBS as an indirect source of Br dot to prevent the competing electrophilic addition with Br2. And at the end, we discuss the HBr addition onto the double bond with peroxide. It's a different type of radical mechanism and hence different kind of selectivity as comparing with the electrophilic addition of HBr with alkene. Right. In our next lecture, we'll see nucleophilic substitution reaction via two different reaction mechanisms on next Monday. So this is the end of my chapter 8. I'll post the end of chapter 8 questions later on today. And I'll have to run, so I